The Kinetic Molecular Theory by Mihika and Kyra. When we talk about the kinetic molecular theory, let us first review the properties of gases. Gases have 5 key properties. The first is indefinite volume, meaning they do not have a certain volume to which they can form. The second is indefinite shape, meaning they do not have a specific shape they take. The third is gases are compressible, they are able to be compressed. And fourth, they have low densities. Fifth is they are constantly in motion.
So what is the kinetic molecular theory and why is it important? The kinetic molecular theory is a set of 4 postulates, or rules, that can be used to explain many characteristics of gases.
Postulate 1 states that tiny particles separated by large distances make up a gas. Because of these large distances and minuscule particles, each particle is so small compared to the total volume of the gas, that the volume of each particle is assumed to not matter or to be 0. This means that most of the volume of a gas is occupied by the empty space between the small particles.
Here's a visual representation of the first postulate of the kinetic molecular theory. Imagine we have a sample of gas under a microscope, and let each small purple dot represent a gas molecule. As we can see, each molecule is far apart, unlike a solid or a liquid where they would be close together.
The second postulate describes the relationship between movement and gases. It states that all of the particles are in constant and random motion. Essentially, they never stop moving. This means that the particles will always take a straight line path unless collisions occur with other particles or the walls of the container.
Going back to our visual representation, we can add in the second postulate by drawing in arrows to represent that the molecules are in constant motion. Notice that they are all going in different directions to represent that their motion is random and that they are traveling in a straight line.
The third postulate identifies how attractions and repulsions between particles are negligible, meaning they take no significance in the relation of a gas. This means that, much unlike solids and liquids, gas particles do not stick together. This is because attractions are negligible and therefore particles don't feel the attraction. The fourth postulate relates temperature to average kinetic energy. It states that the average kinetic energy of the particle is directly related to their temperature in Kelvin, meaning that one increases, the other will increase. This means that the higher the temperature in Kelvin, the higher the kinetic energy, and vice versa. The lower the temperature in Kelvin, the lower the kinetic energy.
Let's go back to our visual representation. According to the kinetic molecular theory, the lower the temperature in Kelvin, the lower the kinetic energy of a gas, and the higher the temperature, the higher the kinetic energy. So at 100 degrees Kelvin, the kinetic energy of our gas sample might look something like this. But at 20 degrees Kelvin, it might look something more like this. To wrap up, we'll talk through some examples of how the kinetic molecular theory can be used to describe some of the properties of gases. Gases have much lower densities than solids and liquids because the particles are separated by large distances, so a large volume of gas will only have a small mass. Additionally, attractions between particles are negligible, so they will not stick together like liquid and solid molecules, making the density much lower. Charles's law is a law that states that the temperature and volume of a gas are directly related, so as one increases, so does the other. According to the fourth postulate of the kinetic molecular theory, the average kinetic energy of a gas is directly related to its temperature. So as the temperature increases, the average kinetic energy of the molecules increases, causing them to collide against the container walls more often and increasing the volume of the container. Thanks for watching. Hope this video helped.